Hello, Cognitect. My name is Cole Frederick. I teach and study algorithms at Colorado State. I'm something of an independent developer, and I've been working on first-class access to the Edn data model from multiple languages. I'd like to tell you about why this is something I wanted, what problems I was trying to solve, how this relates to your business, and some of the trade-offs and choices I faced along the way. A bit about me. I like to take things apart, see how they work. I'm very curious. I do a lot of learning, and I sort of follow my nose here. I love things like languages, VM technology, garbage collection, OS level stuff like virtual memory. I've implemented a variety of math algorithms like matrix stuff, recursive things, big num, cryptography, all a lot of fun. I had an interesting project building an add-on to Node.js, bridging to a C++ sort of statistical modeling library. And it was really interesting to see this dynamic runtime being implemented in terms of C++. I've done lots of projects that need to gather data, aggregate, make little decisions or coordinate activities. I've also done a lot of projects generating data. So in my sort of computer science career, I started off in imperative and statically typed languages like C, and I was very excited when I found Lisp. The old writings and starting to work in Common Lisp was really interesting and really different. The dynamic interaction and kind of higher level concepts like metaprogramming. So I was having a lot of fun, learning a lot in that time. About a year and a half later, I came across Clojure and I fell into Clojure. I wasn't sure what to think about it at first. I was pretty attached to Common Lisp. I was not sure why we would need something else. But I really loved the technology, and I was really inspired by the teaching materials that you guys have made, and the videos that Rich has done, etc. I hadn't done this kind of functional programming before, and this was really different to see how to phrase programs in this way and learn how to do things the Clojure way. But when I kind of got my head around that, I turned this approach on sort of problems I had done in other languages. I kind of knew those domains, and I was crushed to find that those problems were tiny. I thought I was sort of, fighting the good fight. A weekend project now was like a 2-line Clojure program that could be kind of built up interactively, piece at a time. So I felt a bit silly. I also was sad because I felt I had wasted a lot of my own time doing other things. The upside of this, though, was that I could start taking on harder problems, and I did. And project by project, taking on bigger and bigger problems, I learned a lot. And years have passed since, and this has definitely changed my career, learning Clojure. And I want to thank you guys for the work you've done and materials around it and interviews and whatever. Has been really important. But I had a problem, and I came to talk to you guys about the problem. Even though I had Clojure and I was applying it to more and more interesting problems all the time, having successes with it, still at work I was having trouble often using values to solve problems. So what does this mean? What kinds of problems wouldn't admit to being solved by values? So what was I doing for work? I was teaching mostly. I've done a ton of this, and it's really informed my experience. I've done maybe 5 or 6 years of teaching, 2 to 3 classes a year, 20 to 100 students per class. And I've been really lucky to spend a lot of this teaching time helping people solve problems, helping people program. And I love this part of the job. It's kind of a interactive kind of engagement with the student, trying to see where they are. Sometimes they're not even clear exactly what they want to happen, and that's an important step to take them through. I also want to see what they think is happening if they're trying to debug. I want to see what their mental model is for what's happening, and maybe we can debug that mental model. Try some experiments that will tease out the details of what's actually happening. And a lot of times there's interesting bugs, and I'm right there along with the student trying to figure out what's going on too. So it's sort of a debugging exercise. And I have done tons of this, and I think it's been really helpful practicing these skills and seeing how people learn and seeing how people try to take on problem solving and can learn it over time as a skill. Another large part is evaluating student code. So there's going to be an assignment, and some body of code is the student's portion, and then we're going to want to run it somehow and get some sort of feedback or a number out. I've done this at all different levels, from where I'm maintaining maybe an assignment that was previously designed or adding on or fixing something, through to where I had more control. I was kind of helping the professor design maybe a new assignment, all the way through to where I got to try my own ideas and make my own mistakes. And so I've seen a lot of different ideas here, a lot of different techniques that people have tried, and I've kind of seen how they've worked out. The old standby, of course, is example tests, and these are really low reward for your input. It's really hard to scale these things, and you're often trying to do this against, in my experience, what I found for these assignments was like an object API that the assignment creator had decided on. And so often this looked like sort of driving a state machine along and then verifying that it drove to the right place. It's hard to test much of the state space this way. It's not the best. What you'd really like to do is make a way to sort of parameterize it by data. You'd like to be able to get data in, kind of run student code with it and get data out, and you'd like to be able to sort of parameterize it. So sort of the classic next step here, and sort of the old Unix thing, is make it a program. Make it do a transformation of standard in to standard out, and that's the interface on what the students are going to do. And what I've seen of this is it's hard if you don't, if you're not very conscientious making these choices. It's really easy to get into bespoke formats. I've done tons of manual parsing to support said formats. And at the end of the day, you're not really getting a rich data model often. You're really getting, arrays of ints or something like that. And this encourages students to use printing. Printing definitely has some problems in their learning. It complex the execution trace with computing an answer, and this is why we like print line debugging, is for this exact reason. But here I'd like to pull these steps apart. I'd like to do part of it is computing an answer, and then there's a second stage, which is take the answer and turn it into bytes. So I'd like to separate those. And once we're into using printing, we've got like a format string. I think it's just too tempting for us to like put little tidbits into that format string that aren't about the data. It's just added noise and makes for more manual parsing. So over time, what I've discovered here is that using values is really powerful. We can break up this whole test life cycle into creating the input somehow in some language at some time, and then at some point running the program on it, and then sometime later in some language evaluating the output. And this is really strong. Not all things that you want the students to do can be phrased as these functions, but a lot can. a lot of interesting things can be, and so this is powerful. In fact, those text streams we were talking about before, the Unix thing, they're useful precisely because they are values. Like, at least you can get them to and from a file, and languages kind of agree on, kind of what they mean here. The problem, though, is they're sort of like the lowest common denominator, like the least interesting possible value, because they don't really mean anything. At least we can get the bits back and like restore them, and they cross languages, but they don't mean anything. So we always want to give meaning to the bytes as a second step, and then we're in the format game, and a lot of formats are just custom purpose for a particular use, and even the formats that are more specified often have really diverse goals, and facilitate this in different ways. Once you move to using values, generative testing becomes possible. It's really hard to think about generatively testing sort of like an object model API. But once you're using values, this is straightforward and very powerful. So during this time, what else was I doing? I was doing my own homework as part of kind of my professional career here, and I did work in these standard languages. They were dictated by the assignment. Part of the assignment was you're going to make a program in Python. Oftentimes my experience was that the assignment designer had a data structure model or a class model in mind, and then decided that the interface between the student code and the testing code would be along that model divide. So it kind of meant you were playing their game, unfortunately, and these were often stateful designs, so you were on the hitch for that. I think there were what I saw was a lot of custom APIs, things that didn't connect with anything else, didn't really make sense anywhere else, and so it was hard to retarget these components. It was hard to make other things that matched up with them. And it was hard to pull apart systems. What I found over years of doing this is that I was repeating a lot of work. I was getting faster at like typing it in, but it was very repetitious. I wasn't getting much reuse over time, and basically every time I came to a new domain, a new problem, I was making a custom-built, custom-purpose solution for that thing. So this is really hard. I'd like to identify these challenges that I think afflict most languages. There's a big challenge in supporting rich dynamic data. It's a challenge to do generic data manipulation, have an ability to read and write things in like a rich way, so you're not losing a lot of the meaning in the cycle. And managing state is really hard in a lot of places. You just don't have good tools in a lot of languages for doing this well. And especially once you get into using aggregates, a lot of languages are only going to supply you ephemeral aggregates, and now managing that state is very manual and tricky to get right. So my conclusion, after having worked elbow to elbow, problem solving with hundreds of students, grad students, PhDs, people coming back from successful careers in industry, software production, professors, is that this is just too hard for us to reason about. The tools and the techniques that we're using lead us in directions where most of our effort is going into things that aren't about the problem we were set out to solve, these incidental things. I think we're encouraged to use sort of a mutation simulation style, and that's particularly bad for accomplishing a lot of the things that we want to do in our software. I think we end up with tons of non-interoperable things, more and more specific things, and our tools help us along this way. And our languages are not helping us much in support of information processing, generic tools. Basically, we have simulation, not information tools in a lot of places. So the solution, just use values. It's a big shift away from machinery and a simulation kind of orientation to what's going on inside the computer to calculation, computation. And we're going to move from specific things to general things. Values stand over time. We can share them with other parts of our program. We can convey them, through pipes, through files to other languages. And having interfaces that are largely passing values is the way that we get a great deal of independence between our subsystems. But I work in languages that don't have good support for values. When I was working on other people's designs, the languages were fixed. Often as I was teaching, it was part of the curricula that I was assigned to teach students about, programming in this language or that language. So my main thesis for today is even when I'm working in languages other than Clojure, I still want values. In the spirit of the Edn data model, I want the in-memory data structures, especially the trees. I want to be able to read and write. I want to be able to break up subsystems. I want to make those interfaces. And I want to start making systems that can grow their parts and change their parts without having to coordinate. I want independent pieces. So this is really powerful. I want this when I'm working in Python. And I want other people to have these abilities to work with values. I'm thinking about especially sort of all of my students. I saw a lot of struggle over time, and a lot of struggle on unnecessary pain points. And I would like people just starting out, maybe they don't know enough to shop around languages. I'd like them to be able to use values even in whatever language they sort of were dropped into. Also, professionals come to projects late stage all the time, and it would be really nice if your task was to, say, maintain this thing or add on functionality or maybe start pulling it apart, that you could work with values, even in that other language. So that's my side of it. How does this enable Cognitect? Well, Clojure programmers, people who are already familiar with using the Edn data model to solve problems, with my project can apply their experience in new places because I'm trying to provide values in more languages so that experience is applicable in more places. The configuration for my project that I'm targeting is sort of like a C level API, different architectures, also WebAssembly I'll talk about more, but a low feature VM that's embedded in browsers. And with these kinds of things, I think it becomes interesting to think about compilers emitting code which is largely calls into this value library. I think that could be a very powerful compile target. I think when you're building systems, you're going to have different components that will want to do value processing. And for these different components, you might be working with different trade-offs, and having some options here might be nice. I think especially my project is well suited for small things like AWS Lambda, scripting, low power devices where you'd still like to work with values, and this gives a way to do that nicely. I think this gives a great way to introduce more people to the Edn data model because we can bring the Edn data model to them in their language. And I think other languages, we can now think about them connecting with Clojure systems in a much tighter way. And in particular, I'm thinking about datomic peer implementations that would run in different languages. So the high-level approach, I've got some restrictions. It's just me that's working on this. It's just something I decided to do, and I had an idea in my head of a couple years to something interesting. This isn't like a 10-year plan. These constraints on the time put into the project were a major pressure towards simplifying the constructs I was using and my model for these things, because I needed to be able to understand it in a somewhat small period of time. So if you're going to think about doing this, doing values sort of across languages, the first thing to note is that they're going to vary a lot in how they'll want to do polymorphism, say, or memory management is going to differ across languages significantly. So what are some strategies you might consider? You could go around per host and think about taking Python or whatever, C, and kind of patching up to the level where you have the functionality desired to support the Edn data model. Say, for instance, C, though, it's really not helping you out much, so you're doing almost all the heavy lifting. You could think about bridging to Clojure. A library could start up a Clojure instance and then sort of delegate all operations as sort of like remote calls against Clojure objects. I'm not sure if that's particularly satisfying, but I think it could work. You could think about specifying the algorithms maybe for these persistent trees in some sort of meta language and have that kind of compile into libraries in all these different languages. It's like a transpiler like HAX. I think there's hard problems being solved in sort of that magic transpile step. Doing memory management in all these different languages is tricky, and I think I'd have to kind of see it to believe it, how you could get a tool like that to give the results that I'm looking for. So coming back to patching up C, where we were kind of doing most of the work by patch, we could think about taking a holistic design and saying, if we're not going to assume much from the host, we're not going to really take advantage of much host facilities, we could think about a hostless library. And because it's not using much from the host, it's now more transportable between host languages. So the hardest problem here is that the persistent data structures, the wide branching factor trees, require runtime dynamic aliasing of memory. So more than one pointer to a block of memory. And once you have runtime dynamic aliasing, you need some facility to do runtime dynamic memory recycling. You just can't determine it statically anymore. It has to be done at runtime. There's two basic ways of thinking about doing this. One is in implicit aliasing. Aliasing a piece of memory, copying a pointer, is implicit. You don't make a special event, you just copy the pointer. And similarly, when you're done with a pointer, you just forget about it. There's no special event. So since these actions are implicit, then recycling needs to happen occasionally in sort of triggered sweeps. And this works great. Implementing one is challenging, though. We've seen great results from, say, like the JVM and the engineers working on that, and they've really leveraged some interesting tricks with the interaction between, garbage collection, recycling activity, and thread scheduling and GC safe points, the layout of the stack, making it introspectable for roots, and it even comes into the code text sometimes. The JIT will need to emit, barriers to facilitate the recycling activity. So I'm now thinking about doing that sort of as a library that would want to plug into different languages. I really couldn't do things like stack scanning. So you're left without some of these tricks. It's really hard to think about getting good performance here. The other way, explicit aliasing. When the program wants to alias a piece of memory, make a copy of a pointer, we're going to make some sort of explicit event to mark that, action. Basically, we're talking about maintaining alias counts, reference counts. Similarly, when you go to delete an alias, we'll make that explicit, and that will decrement a reference count. So now, memory can be reclaimed at runtime. We can recycle it when the alias count reaches 0. This actually works okay as a library. It can be driven by other code. Some trade-offs that come along with it. We can't do cyclic structures. That's not a problem for me. I just want trees. Traditionally, there's been a lot of concern over space overhead for storing these counts. I think that's very important with con cells and not so important with the arrays that I allocate. Updating the counts themselves, those increment, decrement operations, the aliasing and unaliasing, that definitely has latency. And when you get into multi-threading, the increments and decrements need to be atomic, and that means locking a cache line. So that has a definite cost. And if you're doing multi-threading and 2 cores are changing the alias count, it'll cause a flush of that cache line between cores, even though they may not be modifying any content. Maybe they're both just reading the content. Sort of unfortunate then that modifying the counts causes us to flush what otherwise was good content. Because it's not batched, it's tightly interleaved with the logical application activity that puts in pressure on the instruction cache versus batching. And because we're not combining this with like a moving compacting collector system, you're left with traditional malloc strategies. So that puts pressure on the data cache. On the other hand, we can now detect unaliased memory at runtime. So this is an alias count of 1, and this is a special condition. We know from Clojure that while birthing a new data structure, sort of like a new array or something, we can update that array in place, and we know it's not going to disturb anyone's view. The effects are going to be local. Because we just knew that memory, we know there isn't anyone else, the memory is unaliased. If we could detect that at runtime, we could think about algorithms that would like to change a tree, like grow the tree, could, instead of maybe copying out everything, detect unaliased memory and just update it in place when possible. And it could do that without interfering with anyone else, the effects being local. It does mean that semantically these are consuming the input value. It's a handoff of ownership from the caller of the algorithm, handing off ownership to the algorithm that's doing that change, which then is computing an answer to give back. So this has the semantics of consuming the input value. So how does this jive with functional programming? Well, linear handoffs aren't enough. We want to be able to say, remember this state of the tree and calculate other states of similar trees. And so we need branching in our sort of version history. So we need a way to split. So there's an algorithm to split one value into 2 equal values that then could go their separate directions. And this amounts to incrementing an alias count to record that now 2 people need this to be stable. User code under the scheme is completely independent of this optimization. So the user code that's interacting, calling into sort of my library code, doesn't care. It's only concerned with the logical changes, the logic of the application. This optimization is only considered in the library code, and it's totally transparent. The library code produces the requested value, copying as much as it has to make sure it doesn't interfere with anybody else's view. And this has the effect that memory, which is to say a tree of memory on the heap, is stable. Its contents don't change while you hold on to a pointer to the root. And this is a great property. The alias counts can change, but the logical contents won't. And this stability of the state of memory over time is going to be critical for building values on this. So with that in mind, I think this is a great fit for things like Python. They're already doing reference counting, and so they can call my destructors with the C interface. And things like Python, there are languages that aren't reference counted, but do have a finalizer hook that could call my destructors and want to interface with C. And so languages like Go kind of fall into here. I'm really interested in WebAssembly runtimes as targets for this. WebAssembly is a virtual machine that is sort of only providing very basic facilities, such as some way to address memory and then a way to kind of glue together stack frames. And importantly, it's integrated into browsers, and now it's working its way into sort of server-side languages with Node.js, of course, has a little WebAssembly sandbox. And there are projects now to get WebAssembly sandboxes in multiple languages, so they can run their own sandboxes, from whatever language. Also, I think this is a nice fit for sort of, raw pointer access style languages. So like C, I think this works well for C. The programmer does have to insert destructor calls, but this is a local analysis. You're just looking for where something falls out of scope. So this is not undoable. Languages like C++ and Rust have a resource model kind of baked into the type system, and they can automate inserting those destructor calls when they go out of scope. And so that's great. At this point, I'd like to kind of compare trajectories of my project and maybe similar things. Clojure is a hosted language. It is really seeking to integrate deeply with the host platform and really get the power out of doing that. It's as powerful as the host platform. It's exposing all of that, and you've got maybe now a better way even to use it, because you've got values and you've got Lisp on top of that. And so it's going to want to share a lot with the host platform, especially in terms of things like memory management and object model. My project, in contrast, is a hostless library trying to plug into different languages. It's trying to bring its own facilities, core facilities like polymorphism, layout on the heap, string. It's going to bring its own string. And it has a distinct memory model, distinct from any particular host. So, other things that might sound similar at first blush, type theorists call these linear types when you have a handoff, and then that guy could hand it off and hand off and hand off. They call this linear types. The linear type theorist guys are really focused mostly on things where the linear history is important for the semantics of use, like you're passing around like a file system handle, so it doesn't make sense to be able to diverge in the histories. I really want branching because I'm trying to do values, so that's a difference. They're also not thinking about using this as a layer on top of a runtime dynamic system. They like the fact that this doesn't need garbage collection, that they know they can insert the destructor at the right time. And I think you get a lot of power from combining it with memory recycling so that you can do things like persistent data structures. There are a lot of libraries for parsing Edn in various different languages, and that seems like that's kind of in the same ballpark here. I would say that these projects are seeking to parse Edn and then bring it, map it into sort of the host language's model, which means a lot of times these are mapping to host types, which you may lose some fidelity. Oftentimes you're not getting persistent aggregates. They're trying to bring Edn towards the language that they're working in. There are also libraries for doing persistent data structures in various languages, and that's definitely a component of this. I would say that from what I've seen, these projects are not really thinking about the life cycle outside of in-memory. They're not thinking about read print, and they're not often thinking about making a general purpose dynamic data structure. Oftentimes they're emulating the standard libraries of the languages they're coming from, and so they're using sort of templating and generics, which makes it harder to use them dynamically. There are also things like Clojure-inspired languages. These are often more like Clojure lookalike languages. They use sort of the syntax of Clojure, but the runtime semantics are significantly different. And in particular, they're not thinking about persistent data structures. So I think this bears interesting resemblance to SQLite. So that's the project by Dr. Richard Hipp. It's a C library that can be accessed from a ton of different languages to read a local file and do like SQL database access on that local file. So it's in C, but it's implementing dynamic types, and interestingly reminds me of Datomic because it is bringing the database in process. And the database, then it can expose access to parts of the database in like a local way, which is interesting. So more of the nitty-gritty, how are we going to do this? I'd like a uniform view of memory, yet I'd like to support two addressing modes, 32-bit and 64-bit. 32-bit really mostly for WebAssembly. They chose to make WebAssembly 32-bit for the density of linked structures at the cost of these programs can't address huge amounts of memory, which is often a good trade-off for things like websites. In order to support them both, I define a base, which is address sized, called the unit. So a unit of memory is enough bits to hold an address. And then for using memory laid out on the heap, I'm going to use an array of units. That's going to be the fundamental base construct. And these arrays are going to be self-describing. They're going to record their size and record the alias count. So I call that a segment of memory allocated on the heap. It has access like you might expect from an array. You can get and set by index. Because it's self-descriptive, it can do bounds checking on the index access, and on trying to set a memory location, it can check to make sure that it's not aliased. As we said, we didn't want to do that. If it's shared, we don't want to update it in place. So we can check that. There's a little drawing over here, a pictorial representation of a segment. So it's an array of units. It's got a special unit at the front, which is the anchor unit that holds that self-descriptive information, and then these square units after are where you'd stick data. Okay, so these are like the contents. So there's an API around doing aliasing, so you can alias a segment that has the effect of incrementing the count. You can ask if it's aliased, like is this safe to mutate in place, basically. And you can unalias a segment, which decrements the count and then returns to you telling you if you're the last guy out or not. So should you recycle this or not? In order to represent a value, I want them to all be uniform sized. So I'm just going to use a unit to represent a value. And so unit, that bit pattern is either going to be odd or even. And so if it's odd, the rest of the bits are an immediate encoded value. So these are like sentinel values and small ints. Could be used or can be encoded this way. And then if the unit is even, then it is the address of a segment on the heap. So say for instance this segment here represents a value, and so in order to do that polymorphically, the first unit is the prism unit, and that's like the vtable pointer. It's access to a type-specific implementation of the requested operation. So that's how all values on the heap start out. That interface I just mentioned that everyone implements, it has things for basic like object access, equals and print and hash. And it has things for supporting aggregates and supporting numbers and doing type identification. So the vector tree, it starts off empty. It looks like this. It's the empty one is a segment. It has the anchor here. It has the prism redirecting to vector-specific implementation, and it's got this hamburger bar unit here. This is the guide unit. It's where we store like the count of the vector and like the hash. And then you'll notice the white blocks after this. This is like buffer space. So if we go conj an item into the vector, it'll go right here in the first buffer space. Conjing a second would move us to this state. Conjing a third would move us to this state. Conjing a fourth. At this point, we need to grow, reallocate the backing store here. And then we'd put in the fifth, conj the sixth, and seventh and eighth. It's time to grow again. The ninth would go here, and the 10th, and so on. We're full up to 16 here, and we've reached a critical point. The vector tree is parameterized by a constant to tell it to be 32 arity or 16 arity. It ends up that 16 is easier to draw on the screen. So that's what we're seeing here, is a 16 arity tree. So it's reached a critical point because now it needs to grow a tail. So we will allocate a segment to act as the tail. We'll put the 17th element right there, and we'll link the tail into the root segment. And then we'll start filling up the tail one by one. When that tail is full, it's time for the tree to grow in height. So the root contents are moved out into their own child segment, and the tail, the full tail, it becomes the second child segment, and we start a third tail empty and put the 33rd item there. So conjing, continuing to conj, that tail would fill up, and the next conj it would become a child itself, and we'd start a empty tail, start a new tail. Once we've filled up 16 of these tails and we've got a full tail coming off the root, it's time for the tree to grow in height again with one more conj. And so we would copy the root contents out into its own segment and make a path down to that tail that needed to come down and start a new tail. If this filled up, we'd start a third one, and so on until we had 16 of these and a full tail, and so the tree is now about to grow in height one more time. So conj grows the vector tree in this direction, and then sort of the opposite is pop. It sort of shrinks the vector tree one at a time. It's the analogous opposite operation. So I also need a list. How is a vector like a list? Well, they're both ordered lists sort of in the other way, though. And in particular, from a list, I don't want a amortized, like add operation. I wouldn't want this to be like a Java util array list where it's going to copy the whole thing. A list, I kind of want it to be somewhat cheap to add things onto it. Well, the vector tree already does these things. So we can just co-op the vector tree for this purpose. We just need to reverse indexing operations and reverse order of looping in the reduction, windowing reduction. So these two types mostly share most of their implementation, which is nice. The other tree is the hash tree, and this supports maps and sets. The hash tree starts out empty, if it's a map looking like this, and we see there's a new unit here. It looks like the top of a Lego. It's the pop unit. It is the bits set to tell which keys and which children are present at a level in the hash tree, and this was what allows the tree to be sparse. So it would start off empty like this, and we'd associ a key value pair into it. It would sit right here, and we'd mark it in the pop unit. We might do it again. It would sit again in the root, and we'd mark it. A third one and a fourth one we imagine come into the root. And then we're ready to add the fifth, but we have no buffer space, and so just like the other tree, it'll reallocate to make space for this. And then the sixth item that we associ, the sixth key we associ, we imagine that it collides in the first level of the hash tree with an existing key, and so we would be forced to use a child segment, a second level in the tree, to resolve that collision. So the growth of the hash tree is sort of chaotic, so let's just fast forward to one that's grown a little bit. So this pop unit describes the root contents, and then we have a block of children and then a block of key value pairs at the root. So now children are, each child is a pop unit describing that child segment and the address of the child segment that we're describing. And so this is sort of recursive, so if there was a conflict in the first two levels of the hash tree, we would do a third level, and so on and so forth. If they collide in all bits of the hash, it just makes like an array list at the leaf. This tree is also parameterized with a constant, so it can be 16 arity or 32 arity. It supports sets by, instead of having a block of key value pairs, it's just a block of keys. So these two types share almost all their code. So the split operation I was kind of talking about before, let's see a visual example. So we're imagining here a vector tree that was then aliased, so somebody called split on it. Now it's aliased. There are two outstanding aliases to it, and so I've colored the anchor darker to show that it's aliased. So one of these aliased vectors wants to grow the vector, so it wants to call conj. Well, it's going to need to make a copy of the root. It's also going to need to make a copy of the tail, and then it can add the new item into the tail. And this means that these two roots now are sharing their children, and so the children are aliased. This process of copying the path from the root down to the point of change can happen as deep as the trees go, and it just traverses the levels, copying as it needs to down the path. So multi-threading, this model still works. Memory is still stable. We just need to use atomics now. What we can get, though, which is interesting, is races between the threads. We just saw that sometimes an algorithm will need to copy stuff out, and then it doesn't need the original anymore because it made its own copy. So a thread could copy out and then go back to the original to say, I don't need this anymore, only to find nobody else did either. So what this means is that the other thread who was holding on to this bailed while this guy was busy copying. And so this guy comes back and he just cleans up. It's interesting to think about exercising these race paths on purpose for testing purposes. The segment is aliased method can return a false positive, say, yeah, it's aliased, when it really isn't. Stimulating the thread to copy out and then come back only to have to clean this one up too. So you can exercise these race paths without trying to make races. So that's nice. Atoms work great. They work great in this model too. There's some trickiness doing multi-threading with atoms, where even reading the atom does require atomic operations now. That's not the end of the world, but something to consider. Handing off these owned resources is a good fit for some operations, but not all. There's a lot of operations that really would just be fine with sort of read access. Printing them, accessing parts of it, answering questions about it. Doesn't really need to consume anything. We could just do with looking. So I'm going to differentiate a value and the address of a value, sort of a pointer to a value. And so this is going to correspond to consuming a resource versus just borrowing it. You've got an address of a value, you're borrowing it for a time. So addresses are never written to the heap. That's just a stack thing. So it's just for gluing together stack frames and parameterizing algorithms that way. So these addresses, these pointers, we can pass them down stack frames. That's fine. Returning pointers up is problematic, but passing them down is always fine. And this is because the lifespans of these stack frames are nested. And so if the value is stable as of a certain stack frame, you can pass that address down to further stack frames and know it'll be stable for their lifetimes as well. But now we've got two types, and that definitely makes complexity, generates complexity in the model for using this. Now, in any places where you needed to figure out which one you wanted, you now have to make a choice. And they do have separate semantics that the programmer now needs to understand the differences between. I don't think this is terrible because addresses are only a stack-only construct. And when you get into trouble, when there's a mismatch, you're not stuck. The most stuck you could ever be is you need to call split on an address to get your own outstanding alias, like an owned resource from that. And going the other way, if you had a value, you could always take the address of it. So it's really easy to convert from one to the other. It's mechanical. So you can't get in too much trouble. You can't get stuck here. Transducers are really important for working with the trees and the model in general. So a transducer is like a constructor for the sort of runtime process, the process that then is ingesting value after value after value. So I'm just going to focus on the process API, sort of like a service provider API. So a process, the interface for that, it's going to have a way to ingest a value, and that's either going to be okay, or categorically we might have like an early reduced triggered state. And then a supplier of these values can signal end of input with a method call, and that says finish up and provide me the final, value. What's happening at runtime is a stack of these processes, each process holding on to the next innermost one. I reify the stack, I make it explicit, and I pass it around in these method calls. What this means is that a process doesn't need to capture the inner reducing function, the next process in the chain, because it's got a stack, it just knows the next guy is, one down. So this makes them less stateful to construct. I also I don't pass the result so far down through the stack of these processes. The reasoning here is that processes are potentially stateful, and the bottommost process, that was the only thing that really knew anything about the result so far and the meaning of it. So if it wants to maintain that kind of state across operations, it can. Because I don't have a result so far that's traveling through the stack, I don't do any sort of init forwarding. It's just not meaningful now. I have a desire to work with reducing mappings, and so there's an analogous ingest key value, which now takes 2. And I would like to support both sort of flavors of processes that may just want to look or borrow or view, and processes that really want to consume and get the efficiency for doing that. So ingest takes a value, and then there's sort of partial ingestion, so that takes the address of a value. And there's something analogous for ingest key value. These mix and match at runtime just transparently. There is code to do mechanical conversion between whatever ends up sitting on top of each other at runtime in the process stack. So that's nice. I have an Edn Reader. It is modeled as a state machine. It is sort of a stack. It keeps like a stack of the in-progress collections. And you drive the state machine forward by offering it a byte array to read out of. And it'll either read something successfully and return it and give an indication of where to start next time, or it may read the whole thing and it's still like in the middle of a vector, and so it just says, feed me more. This is a different style. This is, kind of a push instead of a pull. It takes it away from like a stream, pulling on a stream kind of orientation. And streams sometimes get caught up with I/O outside of the process and like thread blocking. And so this is not in the business of interacting with anything like that. Which means that driving code can drive one of these readers. If it's got a bunch of input data, it can just shovel it all through the reader, byte array at a time until it's done. Or if a driver is maybe just getting a trickle of information like over a socket or something every now and occasionally, it can just feed them as they show up to the reader and leave the reader paused in between, and it pauses cheaply. What about sequences? This was really tough. I struggled to find a satisfying way to fit this in with the rest of the model here, and after about 6 months, I gave up. I don't know if there's a satisfying, way to make this fit. I think one of the really attractive parts about it from Clojure was that it performs really well with like the garbage collection, the generational garbage collection, the JVM. Like ephemeral garbage is cheap. I couldn't figure out a way to do that in a nice way, and so I decided not to promise that at all. And so I don't have sequences. Instead, I have transducers and a model around transducers, and transducers plug into operations like reduce and educe that operate on trees and deductions. Also, I've got plans for channels and iterators, which is really machinery. It's not data itself, but iterators can be made to use transducers. And for some places like, say, C, this might still be the best way for programmers there to connect to do aggregate operations. So which language should I write the logic in, like the logic for these trees and data structures and polymorphism and whatnot? Well, I want to be able to do C-compatible stuff, static and dynamic libraries, so like archives and dilibs or DLLs, that sort of thing. And I want to be able to target common hardware architectures as well as, importantly, WebAssembly. So C definitely would have worked. C, you could definitely do this in C. I chose not to. I chose to do it in Rust, which is a language that lives on the LLVM compiler toolchain. It's expression-oriented at sort of the base of the language. The base constructs are expressions, and I find this very pleasant for expressing a lot of nice algorithms. It has the facility to do stack unwinding, so the stack is partially introspectable, and there are paths that it's laid out so that it can unwind a stack frame and clean up, and then that unwinding can stop somewhere. So it's kind of like a try-catch. This is something you really need the language to do for you. It's hard to do this cleanly without. The compiler really needs to kind of compile that in. So that's nice. And here they kind of took like a holistic view to the language, and so the Rust language has a nice support for, say, libraries. Using libraries and declaring it. It feels like a really modern programming language kind of experience around using the tooling here. It doesn't feel like C, using libraries in C. So this has been kind of a long road now. It's been about 1.5 years since I started on this. I spent about 2 months doing sort of just seeing what was possible in memory recycling, reading research papers there, and then designing the trees and the memory system which supports them. It was definitely a back and forth over many, many months, like the next 9 months. The vector tree, I had several failed attempts where I had drawings on paper. I felt like I understood the critical paths and how to do this, and I went to go implement, and I started implementing, critical algorithms, and found it was just getting too complex. I wasn't going to be able to make this reach, and debug it, right? So I turned back, and I had to think about what was causing, pain in like the constructs I was using programming this, and what parts of my drawings and diagrams I needed more thought going into. What were other cases, other things that could happen. And the second attempt failed similarly. The third attempt, I got there. I connected. And it wasn't pretty, but I was able to refine things after the fact. Refine things as I built out other parts of the tree and applied that experience to building the other tree. And so that was quite nice to get that refined. And then I've spent a good chunk of time thinking about how parsing should work, especially in this context, about plugging into different languages, and figuring out how to model the various atomic types in this memory system. I do lots of drawing and note-taking and sort of flow diagrams. This really helps me think about what I'm doing. So I've got, maybe upwards of like 60 of these photographed in a Google Drive. I definitely couldn't have done this without being able to read about other people's thoughts on a lot of these ideas, and so I want to sort of give a shout out to a lot of other people doing thinking in these areas. I'm certainly not done. I want to prove out the concept of connecting these things and making decent APIs, decent libraries in these other places like C and Python, and being able to run this in WebAssembly. So I want to prove that out. I've left things like numerics like a numeric tower, was not sort of mission critical on this path, and so I'd like to get into that and having a library of transforms around strings, things like iterators over the trees. I already have reduction, so it hasn't been pressing, but I'd like to get there. And transducers, although the base API of the processes is well thought out, how to do things like passing closures between languages and sort of parameterizing transducers in that way and having a library of parameterizable transducers is definitely something that I want. And functions around arrays I think are really interesting. We've seen NumPy is very popular because it's quite useful to be able to have an interactive dynamic environment that can do math on arrays. So I started out with this problem. Even though I had Clojure in my toolkit, I was using it and doing interesting things with it, at work I was struggling to solve problems with values. And this was because I was working in languages that don't really have support for values. Some of them not at all. Some, like Python, get close, but it's still on you to do a lot of manual thinking through, especially how state is going to work. So, in view of that problem, I think this is the solution. First-class access to the Edn data model from multiple languages. I've worked on a hostless library where languages plug in, the library is driven from above, API calls driven from above. The API is basically C-compatible functions, nothing too fancy, and most of these functions are functional in the sense that they're really taking and returning only values and addresses of values. And in C, this might look like, in C we can think of this as sort of like pointer-sized integers, opaque integers. So definitely something, concepts that are transportable across languages. Values are modeled as owned resources that can be transferred, handoff. They're consumed by a lot of the library, kind of functions semantically, and they can be borrowed in the sense of having a pointer to them and pass that down to further stack frames. My project, I think, is sort of true to the Edn data model, having parsing for it. The persistent data structure support at runtime is very important, and having a dynamic execution environment is something that I think is really hard to bolt on later, and so I want to think about dynamism up front. I think a datomic peer library in more languages would be a really interesting thing. Datomic is a nice design, it's very powerful. I'd like to have that kind of logic power in more places. I think this is interesting for language-locked projects, things that are already written in some language. They could become peers, bit at a time. And if you're working on like a new feature in some part of this, Ruby project or something, you could start tapping into Datomic for that part. Need to think about maybe rewriting that into a Java or Clojure or something. Also, I think it's a nice story for polyglot shops, where different people maybe program in different languages or environments. I think I'd like the story here to be, more power to you guys in different places. You guys can use the database in a first-class way from hopefully most of these different places. So I think that makes a nicer story. You could think about maybe rewriting a logic engine, n times, and that would be tedious. I think that the strategy is going to be similar to what I did for values, which is you'd want a logic engine that is reusable and usable, drivable from different languages. And I think you want to build on top of values. You want to build on top of facilities for values. So thinking about what you'd need to build here, support for Freshen, it's always been a goal, and in fact that's sort of how I started out. Was I wanted to make a reader for Freshen, and I think the design work for the Edn Reader, it was always done with the intention of mirroring that style of state machine for the Freshen reader. I think that makes sense there. I've done preliminary design work on sort of like an in-memory B tree, like wide branching factor sorted tree, and I think I'll have a good story around that. The cache hierarchy and the communications parts of this go hand in hand, and I need to flesh that out. And of course the data log engine itself is like a whole subsystem to consider. So why am I contacting Cognitect, you guys, now? I was working, happily before this. I've reached sort of a critical point here where I've been investing a lot of my time, most of my time, into working on this. And because of that, I've been sort of underemployed, like, part-time teaching assistant. And the savings that I did have for this have allowed me to coast for a while. But I've gone, it's amazing that's lasted this long, but it's time for me to sort of get a real job. And in particular because I have large debts to my parents and the government for supporting my education, which I've been working on for a long time now. So I would like to continue to be focused on this project, not have it go to more of like a back burner behind like a full-time job. But I don't have a way to monetize this activity yet. So I contacted you to suggest the possibility that Cognitect might be interested in sort of commissioning the building of datomic peer libraries for different languages. And if you agree that this is something worth doing, I think that I'm a good candidate for doing it. I hope I've showed you that this is something I'm quite interested in, and I've spent a lot of time learning about. I've invested a lot of my time into sort of making this first leg of the project work. I'm sort of in it for the long haul, and I hope I've showed you good design sensibilities in some of the design work I've showed off today. And I haven't really talked about it much. We've been talking sort of high level strategy kind of things, but in the low level, the tactical level, and sort of making the code work, there's a lot that needs to happen to make these things work, and I think I've done a quite nice job with problems in the small as well. So I think I'd be a good candidate for working on a datomic peer library. The project started out, I wanted to read Freshen in a language that did not integrate a garbage collector. And so the name for my project comes from that. I call it Fresh, and I own the domain name Fresh.io. So if you'd like to maybe get together and we could do like a code walkthrough, I'd be really interested in showing you some of the smaller design aspects of this. This was kind of like a highlights reel, the most interesting key points of the design, but there's a lot of other sub-problems that I encountered and solved that were interesting along the way. and really are necessary to make the whole thing work. I'd love to show you some of those more small and subtle aspects to the design of the library, and talk to you guys about the possibility of building new things. So thank you for your time, and look forward to hearing from you.